Welcome back to Math 103. This is video number 13 on measuring power. The task at the end of last time was to write out all the sequential coalitions for the weighted voting system with quota 6 and weights 4, 3, and 2, and then underline the pivotal player in each one. So as always, or as previously, we are denoting the players N, C, and S here, and when we write out the sequential coalitions, what do we get? Well, there's one that looks like this, N followed by C followed by S, and the only way to start with N besides that is to go from N to S to C. So if N is going to be the starting letter, then the only possibilities are N, then C, then S, or N, then S, then C. How about the three-letter words, so to speak, that start with C? Well, there's C, N, S, and C, S, N. Those are the only possibilities if C is going to be the starting letter. And how about starting with S? Well, then the only possibilities are S, N, C, or S, C, N. Okay, so for each of the three possible starting letters, there are only two ways of proceeding from there. That makes a total of 6 different words, so to speak, 6 different three-letter words using these 3 available letters. Now, who is pivotal in each one? Well, in the sequential coalition NCS, when N is the only one voting yes, then N alone can't pass anything. N is not a dictator. When C joins in, N and C have a total of 7 combined votes that does meet the quota, and therefore C is pivotal here. Okay, C is the one whose arrival on the scene as a yes voter makes all the difference, gives enough votes for the coalition thus far to become a winning coalition. How about NSC? Well, N votes yes, nothing doing yet. S joins in, then you've got 4 plus 2 is 6 total weight, and that does just barely meet the quota, so S is pivotal here. The fact that C then joins in, well, that's just piling on. That's not making a difference in whether the proposal passes or not. Okay, we move on to C and S. Well, similarly to NCS, C alone does not have enough votes to pass the motion, but N arrives, and now there's a total of 7 yes votes. That's enough to meet the quota. Okay, but now, when we look at CSN, C casts 3 yes votes, not enough to win. S throws in 2 more yes votes. That's a total of 5 yes votes thus far, and that's not enough. It's only when N arrives that there are now enough yes votes to form a winning coalition. So N is pivotal. N is the one whose arrival makes all the difference to getting the proposal passed. Okay. So S and C, S votes yes, that's 2 votes in favor. N votes yes, that's now a total of 6 votes in favor. So N's arrival makes all the difference. And finally, last scenario, S then C then N. Once again, S does not have enough, S and C together do not have enough, but N is the one who finally casts enough yes votes that collectively they now have enough. Right, so it's not just that whoever votes second in order is the pivotal one, because we see here that since C and S are not a winning coalition, whenever C and S, or S and C in either order, come first, they have to wait until N arrives before they finally have enough votes to win. Having done this analysis, we can look back and notice that, as we expected, there turns out to be exactly one pivotal player in each sequential coalition. One and only one. The exact location of this pivotal player in each sequential coalition is something we had to reason out. It wasn't always the same player in the same spot. Sometimes it was the second player, and sometimes it was the third player in the sequential coalition who turned out to be pivotal. Now, for a system with 3 players, there are 6 sequential coalitions. Now, how could you have known in advance that there would be 6, no more and no fewer? Suppose that for no special reason, just for the heck of it, we decided to write these out vertically rather than horizontally. So we've got our 6 three-letter words, and suppose that we wrote them out vertically instead of horizontally. Does this remind you of anything? Well, perhaps it reminds you of our last chapter, where we wrote out preference ballots, and we thought about the question, with 3 candidates, how many different ways are there you could possibly fill out a preference ballot? Well, there turned out to be 6. And we thought about that 6 number in a very particular way as the result of computing 3 factorial, 3 times 2 times 1. Right? There are 3 people who could possibly be in first choice, or first in a sequential coalition. Having picked who's first, there are 2 ways to pick who's next, and having picked the first 2, there's only 1 choice for who is last on the ballot or last in the sequential coalition. So here's the real mathematical point. Whether you systematically list 3-letter words vertically, as we did in the last chapter, or horizontally, as we are doing now when we write sequential coalitions, the number of those words is going to be the same either way. And now we can answer the crucial question, what fraction of the actual power does each player have in this weighted voting system, according to Shapley and Shubik's approach, which is different from Banzhaf's approach. So if we think, as Shapley and Shubik do, of each instance of being pivotal in a sequential coalition as an instance of exercising actual power, we can ask, what share of actual power does each player have? Well, we count up that there are 1, 2, 3, 4, 5, 6 instances of exercising actual power. The great thing about sequential coalitions is that there's going to be exactly 1 underline in each one. There's 1 instance of exercising actual power for each sequential coalition. So if we know in advance how many sequential coalitions there are, then we know in advance what the denominator will be in all of our fractions. Okay? So each player will have so many sixths of the power, because there are 6 instances of someone exercising power, according to this way of thinking about power. N, Northern Jersey, controls 4 out of those 6. Okay? So that's 2/3, or approximately 66.67% of all the power. Central Jersey controls only 1, and Southern Jersey controls only 1, so they each have 1/6 of the power, or approximately 16.67% of the overall power, the actual power as we're calling it. What we just did was to compute the Shapley-Shubik power index of that particular weighted voting system. So this is another way of measuring each player's actual power in a weighted voting system. And typically it too is expressed as a fraction or percentage of all the power, just as we did with Banzhaf's power index. Okay. So to compute the Shapley-Shubik power index, we do what we just did. We list all the sequential coalitions in the weighted voting system, very important to list all of them, and we underline the pivotal players in each, that is to say the pivotal player in each one. So a particular player's Shapley-Shubik power index equals the number of times that player is pivotal divided by the total number of times someone is pivotal. So note the analogy here to how we computed the Banzhaf power index. In each system, in each way of measuring power, there's a notion of the total number of times that somebody exercised actual power, and we're asking what fraction of that total number of times somebody exercised power, what fraction belongs to that particular player we're looking at. An equivalent way of saying it, and this is now verbatim the same as for Banzhaf, is a particular player's Shapley-Shubik power index equals the number of times that player is underlined divided by the total number of times somebody is underlined. Okay? And it's to emphasize that analogy between the two that we use underlines for both methods. Again, following the same convention as we used with Banzhaf, we use the word power distribution in this case to mean that the Shapley-Shubik power distribution is a listing together of the Shapley-Shubik power index for each player. So this is just gathering up all the information in one place, in one table. Okay. this table answers the question, how is power actually distributed among the players according to the Shapley-Shubik approach? We now have two different methods for answering the same question, so that leads to a follow-up question. Do our analyses of power, of actual power and how it's distributed among the players, do our analyses using the Banzhaf and Shapley-Shubik approaches produce the same results? Maybe they do, maybe they don't. So let's look at what we've got so far. For the weighted voting system with quota 6 and weights 4, 3, and 2, here are our results. Okay? According to Banzhaf, the distribution is 60% to northern Jersey and then 20% each to central and southern. Shapley and Shubik say that it's actually a little bit more than 60%. It's 66 point something percent going to northern Jersey and a little under 17% each going to central and southern. Okay. And independently of which method you use to measure actual power, there was this notion of the share of total weight, and that in turn was based on fraction of total population. That's how we originally set up and motivated this example. That's how it's often motivated in real life. You have this idea that 4/9 of the population should be getting 4/9 of the actual power. Maybe they do, maybe they don't. 3/9 of the population should be getting 3/9 of the power, or 1/3, and 2/9 of the population should be getting 2/9 of the power. And we might have thought that allocating votes in a 4:3:2 ratio would accomplish that. Banzhaf gives one way of assessing the results, and Shapley and Shubik give another way of assessing the results. Now, before going on to the next video, answer the following question. What similarities and differences are there between the conclusions drawn by the two approaches to measuring power? So these are Banzhaf's results, these are the Shapley-Shubik results. Look at these numbers, how they compare to one another, and in particular, how they compare to the share of total weight, i.e. the share of population. These two approaches will reach certain similar conclusions, but will also reach certain different conclusions. Think about and comment on that.